So this is a system used by the Michelson and Morley in their experiment. So in this situation, whole system is moving to the light with velocity of v, capital V, with respect to ethers. Ether does not move. Instead, our Earth is moving to the light with respect to the ether. Light is propagating, starting from the source of the light, and propagating to the light, and meet the beam splitters. Half of the beam is traveling to the straight lines, passing through the beam splitters and go to the mirror edge. And the other half of the light travel to the mirror beads. Both of the light is reflected on each mirrors, mirror edge and mirror beads. And mirror edge reflected, return to the beam splitters. And then it's reflected, go to the observers. The other half of the light is reflected, beam splitters, and travel to the mirror B and reflected on the mirror beads and return to the beam splitter and passing through the beam splitters to go to the observers. And L sub A is a distance between the beam splitter and the mirror edge. L sub B is a distance between the beam splitter to the mirror beads. So nobody knows the relative velocity of the ethers. We assume our Earth is moving to the light with the velocity of the capital V. Okay, because of this experiment, actually the Albert Michelson won the first American Nobel Prize in Physics in 1907. Then we'd like to calculate how long does it take for the light to come to the mirror end and return to the beam splitters. We consider the propagation of light after the light arrives at the beam splitters from the source. So this is a beam splitters. After the light is arrived at the beam splitters, the light is moving to the mirror edge. The whole system is moving to the light. So before the light arrived to the mirror edge, actually original position of the mirror edge is here. Mirror edge is moving to the light. So when the light is arrived at mirror A come to the this position. So total length of the light to travel can be calculated. C times T sub A1. So this is total length the light travel. This length can be calculated. Distance between the beam splitter to the mirror A and the length for the mirror A traveled before the light arrived at the mirror edge. Then from this equation, you can calculate how long does it take for the light to arrive mirror A from the beam splitters. Okay, then we'd like to calculate how long does it take for the light leaving the mirror A to return to the beam splitters. So whole system is moving to the light. So before the light arrived at beam splitters, beam splitter is moving to the light. So this is the length for the beam splitter is moving. So V times T sub S2. So this is the length for the beam splitter is moving, plus the length the light to travel is equal to the L sub A, is the distance between the beam splitter to the mirror A. Then from this equation, you can calculate the T sub A2. So if you sum up these two times, you can calculate total amount of the times for the light to spend to come back to the beam splitters. You can use these calculation. 1 over C minus V plus 1 over C plus V. It becomes 2C over C square minus V square. So it becomes 2 over C. 1 over 1 minus B over C squared. So using these equations, you can write down the T sub A. Then we'd like to calculate the light reflected on the mirror beads. How long does it take for the light leaving the beam splitter to go to the mirror beads and reflect it and return to the beam splitters? This L sub B is the distance between the beam splitters and the mirror beads. This is mirror B. This is beam splitters. And the mirror B is moving to the right because the whole system is moving to the right now. We consider. Then the light have to go to this direction to come to the mirror beads. So while the light travel to the mirror beads, whole system is a beam splitter and the mirror B is moving to the right with a distance of the B times T sub B1. Then this length is the L sub B. You could consider these triangles. Use the Pythagoras theorems. So L sub B squares plus BT sub B1 squares equal CT sub B1 squares. So we use this equation. From this equation, you can calculate T sub B1 equal L sub B over square root C square minus V squares. And the reflected light on the mirror B have to return to the beam splitters. This is very symmetric. Actually, T sub B2 is equal to the T sub B1. So it becomes, we have this equation. The time difference for the light go to the mirror A and the mirror B and return to the beam splitters. So this is a light to go to the mirror A and return to the beam splitters. T sub B is a light to go to the mirror B and return to the beam splitters. And if you calculate the difference between these two times, you have a little bit complicated equations. But you expect there looks like a delta T might be the different from 0. Then difference of the distance can be calculated by multiplying the speed of light. This is speed of light. And then we could expect interference patterns could be observed. The interference. So we study the interference. If the two waves coming to the same regions of the mediums, a crest of one wave meet another crest of the another waves, then we expect a constructive interference. So in this situation, C delta T is the integer multiple of the wavelengths. This is integer. And this is lambda is wavelength. Then we expect a constructive interference. If the C delta T is a half integer multiple of the wavelengths, then we expect a destructive interference. So interference patterns produced by the Michelson-Morley experiment, for example, this is the interference patterns we observed in the single experiment. Then actually we are going to rotate whole system by 90 degrees and we observed what's happening. Originally we considered the whole system is moving to the right. So still keep the whole system is moving to the right. But now system rotating by 90 degrees. We should calculate the time difference for the light to come to the mirror A to return to the beam splitters, and for the light to leave the beam splitter to come to the mirror B and return to the beam splitters. In this situation, delta T becomes a delta T sub 90 degrees. Then these quantities can be calculated with this equation. We could calculate the difference between the delta T and then delta T sub 90 degrees times this is C, the speed of light. These quantities can be calculated. L sub A plus L sub B over C times B over C squared. By changing the L sub A and L sub B, these quantities, we expect a change of the interference pattern. For example, if we observe the constructive interference pattern for the delta T, we might observe the destructive interference pattern for the delta T 90. Then we could hopefully we can measure this V. V is the speed of our Earth relative to ethers. And the observational result is very negative result. No displacement of the interference is observed. No change of interference patterns. So this means this have to be 0. So this is equal to the L sub A plus L sub B over C, B over C squared. This quantity is 0. L sub A, L sub B cannot become 0. C, of course, is not 0. Then we have to conclude B have to be 0. So this means ether does not move relative to the Earth. Then you might think the Earth is very special. It's not. It is more natural to conclude that light does not need any medium to propagate. Okay, this is the end of this session.